Let's revisit the mass spectrum of boron, which we saw earlier. Then we came up with a rough guess for the average atomic mass of boron based on the percent abundance of these two peaks. Let's confirm that these peaks actually represent boron by calculating the average atomic mass using the data from this spectrum. Note that we are only given whole numbers for our molar masses of our isotopes here. Our calculations would be more accurate if we had more significant figures and could carry more decimal places out in our calculator. But many times our spectra will be truncated like this, which is okay, as we're just trying to see how close we will get to the actual value found on the periodic table here. In order to calculate the average atomic mass, we need to determine what the contribution of each isotope would be to the overall mass. We do this by taking the atomic mass of the isotope and multiplying that value by its fractional abundance. This simple product provides the mass contribution of one of our isotopes. This is actually a fractional abundance and not the percent abundance, which we saw in our spectrum. To move from percent abundance to the fraction, you simply divide the percent abundance by 100. If you happen to forget this step, you'll know the minute you review your calculated value. A correctly calculated value will be somewhere near the atomic masses given in the problem. A calculated value using percent abundance instead of the fractional abundance will be very far from the atomic masses given. Since boron has two isotopes, there are two types of atoms that contribute to the overall average atomic mass. The calculation we performed for the first isotope will have to be repeated for the second one. Once we have the individual contributions figured, we simply add them together to determine the average atomic mass. Before we get going on calculating the average atomic mass of boron here, it's worth pointing out that these problems generally involve a lot of decimal places. That's because atomic masses are pretty well known and the instrumentation used to determine abundances is usually pretty precise. So we can get lots of significant figures to carry through our calculation. I encourage you to use all of the values given in a problem and to carry them out through the entire calculation and do not round until the very end. Now let's combine the spectrum we saw earlier with the equation for average atomic mass. Our spectrum tells us that the atomic mass of this first isotope is going to be 10 AMU. I find this value on the x-axis of my spectrum. Usually there will be a series of values on this x-axis. This spectrum has just been minimized for clarity. The percent abundance of the first isotope is 18.7%. This one's labeled clearly on this graph, but if it wasn't, I could get this value using the y-axis, one isotope down. Our second isotope has an atomic mass of 11 AMU, again found on the x-axis. The percent abundance of our second isotope is 81.3%, which again is labeled on the top of this boron 11 peak. These four values identify all of the variables except for the average atomic mass, which I know is what I'm solving for, so I must be ready to complete my calculation. Substituting the values into the equation as they appeared on the spectrum gives us this. Notice that I have included the calculation to move from percent abundance to fractional abundance in the equation itself. You can also do this calculation separately first and then insert the fractional abundances, or you can move the decimal place over twice in your head, which would give you this. I do not expect to see menial calculations such as this anywhere that work might need to be shown. I really do trust that you can move decimal places in your head. I'm simply showing it for the less confident of you. This equation includes the contributions to the whole from both of our two isotopes. You simply determine the product for each isotope, leaving you with two decimal place values, which you sum together, which gives you the average atomic mass. This is about the time that a large portion of our class is going to panic because they aren't sure what to do with their significant figures. If you follow along with my calculations, my sig figs don't really compute. My final answer matches the periodic table entry for boron, but it has little to do with the sig figs from this specific calculation. If you're working in a lab and you're reporting data there, I cannot stress highly enough the importance of getting those sig figs correct. For our lecture, I'm much more concerned that you have enough sig figs in the calculation itself and that you avoid having either a ton or way too few in any reported answer. The easiest way to ensure you have enough in the calculation itself is to include all of the decimal places given in the problem when you're typing things into your calculator. And secondly, to carry out as many places in your calculator as possible until the very end of the calculation. If you're good at using parentheses, then this means that you don't clear your calculator during the calculation. If you're not good at using parentheses, then this just means writing down quite a few values for any intermediate steps. For easy to handle numbers, or those numbers somewhere between the hundredths and the hundreds place, aim for reporting 2 or 3 decimal places on a final answer. Numbers too much bigger or smaller than these will probably need to be written in scientific notation. Avoid reporting answers with a single sig fig, that is too few, unless that is the actual answer, like the 10 AMU that we see in our spectrum here. Also avoid reporting answers that have a bazillion and a half sig figs, because that implies that you are the greatest scientist of all time. And while I am very proud of you, I am not entirely sure that's the case.